So a lot of this has already been described, so I'll try to be brief about what has already been described and try to describe some other topics that have not been described yet. But so all CFD users, both the engineers and the clinicians, need to be aware that there are many assumptions or approximations that are performed, and we need to be aware of those approximations so that we don't over-rely on the simulations, right? So there are some approximations that are well understood by the engineers, which is steady flow, laminar flow, incompressible fluid, rigid walls, mesh sizes that are relatively small. And then there are less understood approximations, which I'll describe, which is the segmentation threshold to build a 3D model, the outlet boundary conditions, the physiological effects of the nasal cycle, how accurate our virtual surgery models really are, and intra-subject variability. So to help with our thinking, I'm proposing this framework here that I think there is a cost-benefit ratio that if we make assumptions of incompressible flow, steady flow, small meshes, we can get faster results. Of course, we can get higher accuracy with unsteady flow, like direct numerical simulations and so on and so forth. And I think from a basic science perspective, we're definitely interested in being as accurate as we can, understanding all the physics of the fluid mechanics of it. I think one open question that maybe we can talk today, but I think will be a long-term discussion for this field, is how accurate do the CFD simulations actually have to be in order to provide clinically relevant results. So Dr. Durley said that patient-specific modeling is challenging, and I agree that if you want to know the exact truth of what the flow is in that patient, it's hard. But when I talk to doctors, they're usually interested in, if I reduce the turbinate by 2 millimeters, is that going to help the patient? Should I do 2 millimeters or 5 millimeters? And I think that doctors probably be happy with saying that if you do 2 millimeters, you get, let's say, a 50% reduction in this patient of, let's say, nasal resistance. In another patient, if you do the same operation, you get like almost no change in nasal resistance. So if we can answer that question, then I think surgeons will be happy about it. So I think that the decision of how accurate we need to be depends on what variables are relevant for clinicians. So one variable, of course, is nasal resistance, which is the slope of the flow versus pressure curve. So as Dr. Indhavong said, based on that Strohel number, which is proportional to the frequency of breathing, we know that the unsteady effects are not dominant for low breathing frequencies and low flow rates. So in this figure here, I'm comparing some experiment flow pressure measurements we did in a plastic model with that were steady, with both steady state simulations and unsteady, which are the triangles. And we basically get the same results for the pressure flow curve for steady and unsteady. So I think that as far as nasal resistance is concerned, steady state simulations are good. On the other hand, there are other variables that we may need to do unsteady simulations. So recently we performed this in vivo measurements of nasal mucosal temperature. And as you can see, during the breathing cycle, the temperature of the nasal mucosa goes up and down. And on the right-hand side here is a comparison of the minimum and maximum, the change in nasal mucosal temperature during a cycle from a quiet breathing to like a deep breath. And you can see that with a deep breath, there's a higher range. So this is something that, if you want to reproduce this, you need unsteady simulations. So as has already been discussed, there's a big debate in the field whether nasal airflow is laminar or turbulent. And so this is more for the clinicians in the room to understand what's the big deal here. So this is a fluid mechanics book, and there's a plot of pressure versus velocity. So velocity is proportional to flow rate in a pipe, so a circular cylinder, right? And you can see that on the left side we have laminar flow where pressure is proportional to flow rate, and then there's this change in the slope, and then the flow becomes transient, transitional, and then afterwards it becomes turbulent. So the slope of the curve in this transitional range, it changes smoothly from the laminar flow to which is the slope of like 1, to a turbulent flow, which is a slope of 1.75. And it turns out that nasal airflow is right in that range of transitional flow, and that's what makes it so challenging. So just briefly, if we want to reproduce nasal valve collapse, of course, rigid walls is a bad assumption. Another common assumption is incompressible fluid, that air density is a constant, but in reality, air density changes with temperature. So if you're breathing air at 0 degrees Celsius, there's about a 12% change based on the ideal gas law for air density from 0 to body temperature. Okay, so those are like the well-understood engineering approximations. So now I just want to briefly discuss some approximations that I think are less described in the literature. So in particular, when I read CFD papers in the literature, oftentimes authors do not report the segmentation threshold used to create the 3D models. So here is a comparison of the 3D geometry being segmented with ranges from minus 1024 to minus 800 Hounsfield units, minus 550, and minus 300 Hounsfield units. So looking from afar, it doesn't look that different, but then you can see on panel B that the white arrows are pointing to the region where the small walls that separate the sinuses are not being properly reconstructed with the minus 800 range. On the other hand, if you go to the minus 300 range, wherever the airway is very narrow, you start to lose those connections, and it looks like there's no airway, but there's actually an airway there. So there's some range that you can get good 3D models, but it's hard to say exactly what reconstruction threshold you should use. So this is like a zoom in near the inferior turbinate just to show that this segmentation threshold, the effect is just about 1 pixel on the image. So it's really, really small. So I think it's often overlooked that this small change can actually lead to pretty significant differences, as I'll show in a minute here. So we did this analysis on 3 different patients. And so these plots show cross-section area versus distance from the nostrils. And you can see that in the turbinate region, we can get as much as like a 1 centimeter squared difference in area, or maybe even 2 centimeters squared difference in area using different thresholds. And that's because the perimeter of the nasal cavity is really long, right? So that small 1 pixel size along that long perimeter leads to a significant change in area. This is now a comparison of the pressure flow or flow pressure curve with some rhinomanometry data in the left cavity on the bottom and the right cavity on the top for the 3 patients. And you can see that comparing to CFD models created with the minus 300, minus 550, and minus 800 Hounsfield units. And you can see how the segmentation threshold can lead to very different nasal resistances or pressure flow curves. Okay, so another topic that I think is often overlooked is the effect of the outlet boundary condition. So oftentimes in the literature, we see people or authors setting a constant pressure in the outlet, oftentimes like a 15 Pascal negative pressure as compared to atmospheric pressure. I think one thing to keep in mind with that is that the geometry of the nasopharynx is very flexible. So the clinicians know this, but I think the engineers often don't know this. So if you get 2 CT scans of the same patient, the nasal cavity will look the same, but oftentimes the nasopharynx looks very different. And since the overall resistance of the model is the nasal cavity resistance plus the nasopharynx resistance, if we're setting this constant pressure drop from the nostrils to the outlet in all the patients, or even the same patient before and after surgery, and then you have different configurations of the soft palate, then that leads to a confounding factor, right? So we did this analysis comparing different outlet boundary conditions in, I think it was a group of 15 patients, if I'm not mistaken. And we compared this Kimball 2013 paper boundary conditions, which were like a patient-specific flow rate that we estimated from body mass versus setting an outlet boundary condition of minus 15 Pascal versus changing the outlet pressure to have 15 Pascal at the end of the septum and versus at the rightmost side, the 15 liters per minute boundary condition. And we quantify the correlation of patient-specific measures, such as the nose scale with CFD, these various CFD variables like flow rate, nasal resistance. And what we found was that the best correlation between the patient-specific subjective measures of nasal obstruction and the CFD variables were obtained by setting a constant flow rate, either with the patient-specific flow rate in the Kimball 2013 paper or the 15 liter per minute flow rate. So because a constant flow rate, you adjust the pressure so that the pressure at the nasopharynx or the configuration of the nasopharynx doesn't play as much a role. Okay, so I just have 1 minute to go. So just quickly here, another issue that engineers often overlook is that the nasal geometry is dynamic, right? So here's a patient that we studied that we have a pre-surgery CT scan on the left side and a post-surgery CT scan on the right side. So this is a coronal cross-section at the back of the nose where no surgery was done in the back of the nose. And you can see this huge mucosal change from left to right due to the nasal cycle. And how do we account for, or how do we quantify the surgical change that is independent of the mucosal change in this patient, right? So in this paper here, we just briefly, we modified the size of the turbinates to reflect the nasal cycle virtually. And then for each CFD variable, we tried to find like a mid-nasal cycle flow rate and nasal resistance, and that improved the correlation as well. So I'm out of time now, and so just one last slide. So historically, a lot of the CFD papers have been based on 1 patient or 2 patients or 5 patients, right? But now we have the ability to build models faster and do a larger cohort. So I think one big question for the future is accounting for inter-individual variability. There's a lot of variability between patients, right? And so in summary, I think there are a lot of questions still to be answered, and in particular need to think about what approximations we can do or get and still get reliable, clinically relevant flow variables. Yeah, thank you.
Klaus Vogt. I'm not a physicist. I'm a dentist and an ENT doctor and maybe a violinist. But I'm dealing since 40 years with this problem, and some of you know me. And there are some basic errors which I wanted, which are going through the history of development of functional methods. And one of them is nasal cycle. Nobody in the world ever has proven that a nasal cycle is really existing. You can prove or test a nasal cycle only if you have some prisoners in a jail sitting on a chair with a rhinomanometer in the same position, writing down when they are laying down, standing up, and without any force. Because the influence of body position and the influence of work is dramatically changing the nasal airway resistance. And even attempts from people which I very well know to do it with equipment which is used by in sleep medicine, then you can make measurements through all the days. We did it. But nothing could be really proven to be something like a circadian cycle. And the other thing is, there's always a discussion, which I do not like, in medical people. Because turbulence in the nose should always something wrong, and laminarity should always something very nice. We have always a mixture of turbulence and laminarity, and it depends not only on the nose, but it depends on the specific place in the breathing cycle. And but what is really very interesting in the moment where you have laminarity or at least a quasi-steady behavior, that is the top of the curve. It means this so-called vertex of the curve, where we have a parallel, for a certain time, parallelly running the flow and the pressure curve, and then you can presume it is really laminar and even steady. Thank you.